All right, so what we're going to do today is we're going to review some problems in chapter 14, about a half an hour or so, and then we'll cover chapter 16. Next week, we will cover on Monday, chapter 17, which we were supposed to cover today. We'll cover that up next Monday. We will also have a quiz on Monday, which covers chapters 14 and 16. And then the following Wednesday, I'm going to cover chapter 19 and also introduce you to an online software program that you're going to be using for the rest of the course called StatKey. So I'll show you how to use that, and we'll begin using that next Wednesday. I will be posting a handout that will show you how to use it, the steps to using it, and it'll replace much of what we usually do in a regular statistics course when we do what's called inference. So but you'll learn more about that next week. All right, so let's go to the online book, ebook. And let's see, actually I don't want you seeing these. All right, so we're going to look at number 9. Now in your book, it's on page 323. All right, now, as you know, there are two types of interpretations of probability, one of which is called relative frequency, the other is called personal probability. And in each of these two scenarios here, determine whether it's relative frequency or personal probability. So the first one says that if a spoon is tossed 10,000 times and lands with a rounded head face up on 3,000 of those times, we would say that the probability of the rounded head landing face up is about 0.30. So is that a relative frequency interpretation, or is it a personal probability interpretation?
Relative frequency.
Relative frequency, that's correct. Because we're doing an experiment. We're not guessing at the probability. We're repeating an experiment over and over again. All right. So as you can see, the answer is relative frequency. And it says here, the method that you're using, well, you're observing the relative frequency, right? You're observing it. Okay. How about B here? In a debate with you, a friend says that she thinks there's a 50-50 chance that God exists. Is that relative frequency or personal probability?
Personal probability.
Yeah, obviously, yes. So personal probability is based on your own belief system. And it's, of course, subject to different types of biases and so forth. And that's what we're going to talk about in chapter 16. But before that, we have some more problems to look at. Let's look at number 11. All right, we're supposed to use the probability rules that we used in this chapter, in chapter 14, right? There were, I think, 4 rules. According to the U.S. Census Bureau in 2012, the probability that a randomly selected child in the United States was living with his or her mother as a sole parent was 0.244, and with his or her father as a sole parent was 0.040. What was the probability that a child was living with just one parent, and what would be your answer? Nobody has an answer for that one?
The relative?
Just part A, 11 part A. Okay. If you just have one parent, let's assume no other person, like no grandparents or anybody else. What are our choices?
I think you have to add up both of them, correct? Add up
Right, you're going to add up those two individual probabilities. So what's your answer?
0.284.
Right. Those two events, by the way, are what do we call them when we can add them up like this? They are two words for that. Mutually exclusive, right? Either the mom is the sole parent or the dad's the sole parent. That's it. They're mutually exclusive. They can't occur at the same time if there's only one parent. So that's why we can add up those two probabilities, because it's asking what's the probability the child was living with one parent. That means either the mom or, where or means add, the dad. So we add up these two numbers. All right, part B. In 2010, in the US, the probability that the birth would result in twins was 0.0331, and the probability of the birth would result in triplets or more than triplets was 0.0014. What was the probability that a birth in 2010 resulted in a single child being born? So what's your answer for that one?
Honestly, if we can go over how to get the answers to this problem, it could help because it's not that I don't have the answer to give back to you. I just don't know how to get there.
Well, that's why I'm asking you first.
Do you add it
Don't
up?
come back and say, how do you do it? I want you to try it first. I'll show you how to do it, but I don't want to just show you right now. I want you to try it.
Do you add them just like how you added the other one?
All right. Now, when we add them, what do we come up with? What's the probability of what when we add those two numbers?
0.0345.
I know, but what are we coming up with? What in words? What is the probability of what? What probability are we coming up with when we add those two numbers?
That the birth resulted in a single child.
Okay. Why would you think that if we're adding up probabilities for twins and triplets or more, why would you think the addition of those two would be for single child? I want you to, all right, I'm going to rephrase the scenario here. Tell me the possible types of births that you can have in terms of what we see in this part B here. What are the types of births that we can have? Forget about boys, girls and boys. I'm talking about the number of children. Give me the types of births. You can have what? How many children?
One is 2 and one is 3, so 5. Like twins is 2, and then you could have triplets. That's 3.
Or you can have more than triplets too, right?
Mm-hmm.
All right. So if I'm adding the probabilities for twins and I'm adding probabilities for triplets or more, what am I ending up with? The probability of what?
Having 2 kids or more.
Having what?
Having 2 kids or more.
Having 2 kids or more. Yeah. Does that make sense? I mean, logically, it should make sense, right? Having twins and having triplets is not the same thing, right? Well, consider them mutually exclusive. So when we add those two together, aren't we getting the probability of having twins or triplets or even more than triplets? Right? Doesn't that make sense when we add those two together? That's what we get.
Would you subtract them both from 1?
Yes. Yes, to get what's left is one child, which is most of the cases, right? Most of the time, a mom has just one child. So when you add those two up, you get 0.0345. What's left is one child. So 1 minus 0.0345 is 0.655. Excuse me, 0.9655. That's the answer to the question. That's why I wanted you guys to figure it out logically, all right, in your own head, instead of relying on me to show you how to do it. All right, logically, summing these two numbers gives you twins, triplets, or more. So to find single child, that's all that's left. You always subtract that from 1. Because 1 says it's certain. It's absolutely certain that you're going to have one child if you give birth. You're going to have one child, you're going to have twins or triplets or more. I can't think of any other possibility, right? You're not going to have fractions of a child, God forbid, right? You're not going to have a negative child. So that's it. So if the sum of these two numbers gives us twins or more children, then 1 minus the sum gives us 1 child. So I want to make sure, I don't know who asked that, wanted me to show you how to do it before, but does that make sense to you? Logically?
Yes, it does.
Good, good. Because I want you to think about things logically instead of formulas. The formulas are there to help you, not to memorize. They're there because this is open book, right? We have open book, open notes. You don't have to memorize anything. So that's why I want you to think about how to go about solving this on your own. And I think you can. All right, let's look at number 12. Now there's a figure here, it says figure 9.1. If you go to figure 9.1, which is chapter 9, it will be a pie chart. All right, and it's basically a pie chart that splits the eye colors of Caucasian girls, all right, into different eye colors. So there's, there's brown and there's other colors, but there's also green and hazel. That's two of the categories. So they're selecting out of this pie chart 2 of them, and they're pulling out that 17.8% of all the Caucasian girls have green eyes. 16.9% of them have hazel eyes. Okay. So the first question is, what's the probability that a randomly selected Caucasian girl will have green eyes? And please answer the question as a proportion, not as a percentage. So how would you answer part A?
0.178.
That's right. To get from a percentage to a proportion, you divide by 100. That's right, 0.178. How about part B? What is the probability that a randomly selected Caucasian girl will have hazel eyes?
0.169.
Correct. So I want you to think about the idea that a probability is not just about a randomly selected person out of the population, but it's also about the percentage or proportion of the whole population that has that characteristic. That is, there's 17.8% of Caucasian girls that have green eyes. Therefore, the probability that we selected one girl, Caucasian girl, out of the population, the probability that girl has green eyes is 0.178. They mean the same thing, all right? We can interpret probability in both those types of ways, either as randomly selected one girl or the proportion of girls in the population. How about C? What's the probability that a randomly selected Caucasian girl will have either green or hazel eyes? Let's assume that both eyes have the same color, all right? I know there are some people out there who have an unusual genetic makeup where they have one eye with one color and the other eye with another color. But let's assume everybody in the population only has one color type of eyes. So what's the probability that green or hazel eyes?
0.347.
That's right. So you add these two percentages and then divide by 100, 0.347. And D is, what's the probability that a randomly selected Caucasian girl will not have either green or hazel eyes? In other words, they have another type of color eye.
.863.
How did you get 0.863?
Oh wait, no, I did the math wrong. Cause isn't it 100 minus 34.7?
Right,
Okay, so yeah, I just did the math wrong.
right. So yes, it's 1 minus, or you could do if you express it as a percentage, you obviously could do it the way you said. Or if you express it as a proportion, it's 1 minus 0.347, which was the sum of these two numbers. And that gives you 0.653. Good. So you're getting it. That's great. All right. Let's move to the next one. The next one would be number 14. Now, I want you to think about this in terms of probability. All right. The rules that we've learned. There's 4 rules. So there's something wrong in each of the following statements based on 1 or 2 of these rules. A, the probability that a randomly selected driver will be wearing a seatbelt is 0.75, whereas the probability that he or she will not be wearing one is 0.30. So what is wrong with that statement?
It adds up to more than 1.
That's right. Right. Remember, the highest probability is 1. And when you have an event like wearing a seatbelt, and then you have another event which says not wearing a seatbelt, those 2 probabilities have to add up to 1. And here, if you add up these 2 numbers, it's bigger than 1. Right? And these are mutually exclusive too, right? I mean, you're either wearing a seatbelt or you're not. You can't be wearing a seatbelt and not wearing a seatbelt at the same time. So they're mutually exclusive, so you would add them up, and then it can never add up to more than 1. All right, how about B? The probability that a randomly selected car is red is 1.2. What's wrong with that statement?
Probability can't be more than 1.
That's correct. All right, now C, the probability that a randomly selected car is red is 0.2, whereas the probability that a randomly selected car is a red sports car is 0.25. What's wrong with that statement?
The red sports car is a subset of a red car, so it can't have a higher probability than like the baseline, the red car.
That's right. That's it. So 0.20 is the probability that a car is red, which would, and then red cars include both sports cars and cars that are not sports cars. So the probability that you have select a red sports car has to be less than 0.20. And in this case, they're saying it's bigger than 0.20. That can't be true. All right. So I'm showing you all this because there is a possibility that in your test, that's the test number 3, I could give you scenarios like this, right? Multiple choice questions, because I'm fond of giving you like 2 or 3 statements and saying which ones are true and which are false. So watch out for these types of situations like this. All right, let's look at number 15. A small business performs a service and then bills its customers. From past experience, 90% of the customers pay their bills within a week. All right. What is the probability that a randomly selected customer will not pay within a week?
Point 1.
That's right. Because if 90% customers pay in a week, what's left? The ones who don't pay in a week, and that's going to be 10% or 0.1. That's right. Let's look at part B. The business has billed 2 customers this week. What is the probability that neither of them will pay within a week? What assumption did you make to compute that probability? Is it a reasonable assumption? All right, anybody have an answer? Well, it's saying that neither you have two customers. So you're selecting two customers at random, right? And they're asking what's the probability that neither of them will pay within a week. So they both pay in a time period that's longer than a week. So what is the probability that one of them will not pay in a week? We just said that. That's part A, right? 0.1. So we're being asked to say, what is the probability that both customers pay in a time period that's longer than a week? Well, are they if they are independent of one another, then we multiply their probabilities. So if neither one of them pay within a week, in each case it's 0.1. So it's 0.1 times 0.1, which is 0.01. So there's only a 1% chance that neither of them will pay within a week. Does that make sense? And the assumption you're making is independence. These two customers are independently making these decisions. So their probabilities are not dependent on one another. What if I ask the following question? See if you can come up with the answer for this one. What's the probability that one of the customers pays within the week and the other doesn't? You have two customers selected at random. What's the probability that one of them pays within a week, but the other one does not? So that's not listed here, but I want you guys to try that one.
Would it be 0.09?
Okay, you're along the right track. You're making the right assumptions there, but it's not complete. Think about all the possibilities that could happen with two customers. Let's call the first customer number one, and we call the second customer number two. All right, so we're looking at them individually. Let's think about one of them paying within a week and the other one not paying within a week. Now, your answer, I don't know who said that, but is along the right track. You're definitely along the right track, but it's not complete. You're missing one little thing. All right. So your answer is good because you're thinking correctly. You're thinking, all right, one customer is paying within a week. That's 0.9. The other customer is not paying within a week. That's 0.1. You multiply those two, you get 0.09, right? But that's only one of two possibilities. That's assuming, let's say customer number one pays within the week and customer number two doesn't. So customer number one, that person's probability is 0.9. Customer number two, that person's probability is 0.1. And you're right, 0.09 when you multiply them. But you forgot about the other possibility. The other possibility is customer number one doesn't pay within the week and customer number two does. So that's 0.1 times 0.9, which is also 0.09. And they're mutually exclusive, aren't they? One event is that customer number one pays within a week and number two doesn't. And the other one, it says customer number one does not pay within a week and customer number two does. So the answer is 0.09 plus 0.09 plus 0.09, and the answer is 0.18. Now, if I had said something like, what is the probability that customer number one pays within a week and customer number two doesn't, then your answer would have been 0.09. But the fact that I didn't say which customer pays within the week and the other one doesn't, I didn't mention which one it is, you have to consider both possibilities and add both of those up. Does that make sense? Whoever answered, that makes sense to you? I hope it does. Now, that's not one of the questions here, but I wanted to ask that question just so that you could think logically again. And I see another student who looks like a feline. All right. The next question is question number 19. This is on page 324. Go to the next one. I think I'm in the right track. Hold on a minute. Yes. It's number 19. On any given day, the probability that a randomly selected adult male in the United States drinks coffee is 0.51, and the probability that he drinks alcohol is 0.31. What assumption would we have to make in order to use rule number 3, that's the multiplication rule, to conclude that the probability that a person drinks both is 0.51 times 0.31, which is 0.158? Do you think that assumption holds in this case? So what assumption are we using here?
That they're independent.
Those two events of drinking coffee and drinking alcohol are independent. Now, is that do you think that is appropriate in this case here, that assumption? Do you think there could be cases where one event could be influencing the other one? Now, in the last class, somebody mentioned that they thought they were independent. Now, this is a matter of opinion, right? Matter of opinion. I think you'd have to do some research, but my guess is that they're not independent. For example, there could be people out there who, after they've drank maybe a few alcoholic beverages, they drink coffee to stay awake. Maybe they're falling asleep or something from drinking too much alcohol. And they want to keep awake so they can drive home. I mean, they shouldn't be driving when they're drinking, but that's what they do. So my guess is that that the probability of coffee does change when a person drinks alcohol, right? It might go up. Somebody might decide to drink coffee. So a matter of opinion. Obviously, that's not something I would ask you on the test because it's a matter of opinion. But whatever you answer here, you'd have to give some rationale for it. All right. Now, let's look at number 32. All right, so this is some sort of version of a lottery game in which a player picks 3 numbers from 1 to 40. And they have to, and then, there's some sort of balls are chosen, and you have to match all 3 of the balls or 2 of the balls, right? Something like that. You only win money if you match 2 balls or 3 balls. You don't match any, or you only match 1 of the balls, you don't win anything. That's what this chart is showing, right? So now it costs you $1 to play. And your job is to calculate your expected gains as a player per game. What's your expected gain per game? And then interpret it. So what I want you to do, I want you to sit down and take a couple minutes and work this out if you can. Remember, a net gain has to do with what? It has to do with an average, right? And we have to take our values and multiply them by their probabilities. But you have to consider here that we're dealing with gains and not exactly what the amount won. So it costs money to play, which is $1 per game. Go ahead and calculate your net gain. The answer has to be a negative number because whoever's running this game, the state of California, has to make money on this. So players overall have to lose money. Anybody have an answer? All right. So let me show you the solution. Stop sharing here for a second. And we'll get to my solutions here. All right, so you can set things up like this. Oops. There we go. Can you see that okay? Yes? Okay. So you would set up, remember we're talking about the variable of interest are gains, right? So what is a gain? Gain is revenues minus costs. So if you win $20, your gain is 19 because it cost you $1 to play the game. 20 minus 1. If you win $2, your gain is $1 because you have to subtract your dollar to play the game. If you don't win anything, then your gain is -1. 0 minus 1 is -1. Here are the probabilities that were for each of the cases. This is for a $20 winning, probability for a $2 winning, and this is the probability of not winning at all. Then you just multiply these values times the probabilities and add them. And notice I put the -1 for the last case inside parentheses and I add it, all right, just so that you know you're adding these products. We end up with -0.486. So it's if you wanted to round this to 40, a loss of 49 cents per game. So if you played this game over the long term, this is what it means. If you played this game over the long term, on average, a player would lose about 49 cents per game. They would win occasionally, maybe over the long term, but overall, it's a losing proposition. All right. Now the casino, now in this case here, if this was a game run by a casino or something like that, maybe this was just a church, some sort of church thing, and they were raising money. So if on average one person's losing $0.486, that means the church per person is gaining $0.486. Okay, does that make sense? All right. Let's look at number 34. Back to the book. It's the last one we'll do. According to the U.S. Census Bureau, in 2012, about 68% of children in the United States were living with both parents. 24.4% were living with mom only. 4% were living with father only. And 3.6% were not living with either mom or dad. What is the expected value for the number of parents a randomly selected child was living with? And how would you interpret that? So, like the previous question, we're being asked for an average. In this case, what is over the long term? What is the average number of parents a randomly selected child is living with? Now, don't round this to a whole number. Just give it as the decimal. The answer has to be between 0 and 2, right? Because either you have no parents, you have one parent, or you have two parents. That's the hint. So figure out the expected amount by doing that. I'll give you a couple minutes to work it out. This is a little more difficult question, but all of you are capable of answering this. And I will post these solutions. I don't know if I have already, but I will. If I haven't, I will be posting all of these solutions. So anybody who wants to review any of this again, they'll have the solutions in Canvas as a PDF. all the formulas and everything. So the solutions include the formulas that I used. All right. I'll move over to the solution. Yeah. Does anybody have an answer? I don't hear anybody, so let's go ahead and look now. All right. Well, there are only three possibilities. You either have no parents that you're living with, you have one parent, or you have two parents. What are the probabilities? Well, they give you probabilities. They give you the percentages, which you can convert to probabilities. 3.6% of them don't have any parents, right? That's 0.0036 with 0 as your number of parents. You have one parent, it's 0.284. Now, where did I get 0.284 from? Well, it is the sum of two probabilities. The probability of living with mom, or the probability of living with dad. So I add those two up, 0.244 plus 0.04, and I get 0.284. Does that make sense? So those are the two possible cases where I'm living with one parent, either mom or dad. And I add up those two probabilities and I put it in here under the 1. And then they say 68% of the children live with both parents. Right? These three probabilities add up to 1, which they should. And I simply multiply the values, the first row numbers times the probabilities. So 0 times 0.036, 1 times 0.284, 2 times 0.68. And I come up with 1.644 parents. Now don't round it, leave it as it is. You're supposed to write it like that. So what this means, number one, is if you have many children, many children, you look and you want to know what are the average number of parents over a population of children. You would say the average is 1.644 parents. It's somewhere between 1 and 2 parents, right? Right. Now you wouldn't answer it, say between 1 and 2. You just say 1.644 parents. All right, and that's called the expected value of the number of parents. Any questions about that one? Not that hard once you see how to do it, right? You have to figure out what your variable is. In this case, number of parents that child lives with. You have to think, all right, 0 or 1 or 2. And then you figure out the probabilities for each case. Either they're given or you have to do a little bit of math to figure out. In this case, it's 0.284 is the sum of 2 of the probabilities given in the question. All right, so these are examples of questions that I could ask on the test, final exam maybe also, on this chapter on probability. Any questions about this, about these questions, about these problems? No? Okay. So I'm going to get now to chapter 16, and we'll go through that. We have about a half an hour to go through this chapter, and there's no calculations or anything in this chapter. Pretty straightforward. Go through this. So actually, as we talked about in this chapter, there are two types of probability interpretations, right? There's the relative frequency approach, and then there's personal probability approach. This chapter deals strictly with the personal probability approach. The relative frequency approach, you just do some calculations, you use those 4 rules, and you come up with your answers. And if everybody's following the same rules, you all get the same answers. But with personal probability, you know, you're talking about the same event. You may come up with different answers to that event based on your own experience and belief systems and all that. So what we're talking about here is the types of influences that could change or bias your personal probability calculations. Okay, so that's what we're going to do in this chapter. Let's see if I can... All right, here we go. All right. So again, we're going to start off with some questions to think about. According to this author here, during the Cold War, which was the time, it wasn't a real war, but it was the time before the breakup of the Soviet Union, where the US and the Soviet Union were chief rivals, nuclear rivals around the world. This was some sort of test. It says plus a check mark besides the alternative that seems most likely to occur within the next 10 years. So this is something that was asked to people who were reading about the US and the Soviet Union. It has to do with nuclear war. First statement says an all-out nuclear war between the US and Russia. That's all it says. The second one says an all-out nuclear war between the US and Russia, in which neither country intends to use nuclear weapons, but both sides are drawn into the conflict by the actions of a country such as Iraq, Libya, Israel, or Pakistan. Now, it says here, using your intuition, pick the more likely event. So which one, I mean, picture just somebody asking a question like this, picture which one of these seems more likely. An all-out nuclear war between the US and Russia, or part 2 there where it explains why there would be a nuclear war. Which is more likely?
The first one.
The first one, okay. Now, is that because you studied chapter 14 and you sort of know the answer?
Yeah, I mean, it's just like the past chapter. Yeah, if you're adding things onto it, like the second option includes, like, is part of like an all-out nuclear war. So the first one is less specific. So the more specific you get, the less likely it's going to be.
That's right. That's actually an excellent explanation. That's really good. But you could picture somebody who has not studied statistics or probability who would pick option number 2, right? Because it's more explanatory, right? And they're thinking, all right, a nuclear war between US and Russia, I don't know. I don't know if that's going to happen. But then based on these additional scenarios, I'm thinking, all right, more likely. I'm going to pick 2. You can picture somebody doing that. But with the rules of probability that we've learned about, we know that option 2 here is a subset of option 1, and therefore should have a smaller probability. But once again, you can understand how people could be biased by the wording here and pick the second option as the more likely. So, all right, let's do number 2. Which is more likely cause of death in the United States, homicide or diabetes? What do you think? Don't think about it too much. Just come up, first thing that comes into your mind, is it homicide or diabetes?
For someone who hasn't studied the chapter yet, it would be homicide because that one has more media coverage.
Absolutely right. That's right. There is a bias that we'll be talking about that has to do with that. And therefore, people in general would say homicide. That's because, like you just said, Julie, that it's more apparent. It's brought to your attention more than diabetes. Unless you have a family member with diabetes, you probably don't know much about it. But diabetes is much more prevalent as a cause of death than homicides. Here's another one. Do you think people are more likely to pay to reduce their risk of an undesirable event from 95% to 90%, or reduce it from 5% to 0? Which is more likely? Or maybe you can even say, what would you prefer? To reduce your risk from 95 to 90% or from 5% to 0? Don't worry about giving correct or not incorrect answers. There's no incorrect answer in this case.
Is it 5% to 0?
Okay. And why did you pick that?
Because if it's something that's not good, they'd rather hear 0 than 90. Does that make sense? That's
Right,
what
so- yeah.
I was thinking that if it's something that's undesirable, then it's better to reducing the risk. It's better to hear 0 than 90%.
Correct. Okay. So this is a type of bias that we'll be talking about. Thank you for explaining it that way. That's exactly the way the bias is explained. All right. Now, if you look at these two possibilities here, in both cases, the risk got reduced by 5%. They do, right? 95 to 90, the difference is 5%. From 5% to 0, that's a difference of 5%. If there was no emotional component to this or any way of interpreting it, you would just say they're equal. But like you just said, 5% to 0, it sounds like a better thing. And I'll explain in a minute why it's so, all right? Why people choose that option as opposed to 95 to 90. All right, let's look at this question. A fraternity consists of 30% freshmen and sophomores and 70% juniors and seniors. Bill is a member of the fraternity. He studies hard, he's well-liked, and he probably will be quite successful when he graduates. Is there any way to tell if Bill is more likely to be a lower classman or an upperclassman? Just read through that, and do you think we should assign probabilities that are different, or should we just assign an equal probability?
I mean, you can still assign a probability. You could just say, but like it has nothing to do with it, that he's in a fraternity, he studies hard. It's just if you pick a random person, it's more likely that they're a upperclassman because there's more upperclassmen.
Good. Okay. Again, you might be influenced by studying chapter 14 as a member of this class, but you can picture somebody ignoring the 30%, 70% after they read about Bill and say, I don't know, I'm not really sure, I'll say 50-50. You could picture somebody saying that, right? And they're ignoring the baseline numbers that were given in the problem. That is something that does happen when people assign personal probabilities. But again, we're studying it, so we're aware that of the 30%, 70% is significant, right? And what you're saying is, well, just ignore all that stuff. Well, let's put it this way. If there was something written in there that gave you a clue that it was a freshman, you might increase your probability from 30% to something higher, wouldn't you? Right? You might say something like they were, in high school recently, within the last couple of years or something. So you might give a higher percent to them being a freshman than 30%. But anyway, but in this case, there's no indication that the person's freshman or junior. So most people would say 50-50, but like you said, well, if we don't know, we should go back to the baseline numbers, 30% and 70%, and say it's more likely the person is a junior and senior. So that's good reasoning. All right, now personal probabilities, once again, are values assigned by individuals based on how likely they think events are to occur. They're based on belief systems. However, we should still follow the rules of probability, right? We still want to make sure the probability is between 0 and 1. If the events are mutually exclusive, we want to add them. If the events are independent of one another, we can multiply them. We still have to follow those same things. And also the subsets, right? If one event is a subset of another, we want to make sure that the probability is lower for the subset than it is for the bigger class of people. All right, so the first type of effect that we're going to look at, or bias, is what's called the certainty effect. People are more willing to pay more to reduce risk from a fixed amount down to 0 than to reduce risk by the same amount when it's not being reduced to 0. So that previous question we talked about from 95 to 90 and from 5 to 0, I think somebody had picked from 5 to 0. That's because of the certainty effect. You're willing to pay a little bit more to have that certainty that there's no risk. So that from 5 to 0 in those people's eyes is a more appealing choice, even though in reality, the two should not be any different in terms of the reduction in risk. In both cases, risk got reduced by 5%. But you were looking at the possibility of reducing the risk to 0. And you felt like that is why I'm willing to pay more. Okay, so this is the whole idea of insurance too. A lot of people want insurance, but maybe they don't really need it because it reduces their risk to 0, right? You know, if you get insurance on your home and it includes some sort of liability insurance that protects you in case somebody, let's say it's there's ice on your payment and somebody slips and falls and breaks their leg and may sue you, their insurance will protect you against that. Well, that's what you may be willing to pay a little bit more for that type of benefit, so that your risk is down to 0. All right, so this is what we mean by the certainty effect. We're willing to pay a little bit more to get our risk to 0. There's also in the book, now I would highly recommend you read the book because it goes into more details. And of course, when I test you, when I do quizzes and tests, I assume that you've read the book, not just read these slides. These slides are just summaries of what's in the book. The book goes into more detail, and I want you to definitely read the book. But again, these slides are here just to help me introduce these topics to you. So pseudo-certainty is like the certainty effect. And this would be an example of pseudo-certainty effect would be something like a warranty on something that you buy. Let's say you're buying a computer or some sort of expensive thing, or maybe your cell phone. And the salesperson's trying to convince you to buy a warranty, which says, okay, if you break this within the first 5 years or something, then we'll replace it, all of that. Well, you can picture having two types of warranties. One type of warranty would say, which is cheaper, would say, all right, we will cover any type of loss, any type of damage, but we'll only we'll only pay for 50%, okay, of the cost. In other words, to get a replacement, you would have to pay 1/2, all right, of the charge. The other possibility would be to pay the full cost of the warranty, not half the warranty cost, and you would get full payment on only some of maybe 50% of the types of losses, and you would not get any payment on the other. Most people would pick that second type of warranty because there's some certainty in terms of the types of losses that they could get. They'd rather have certainty on losses than replacing losses than getting a situation where you're only getting 50% back. So those two warranties, the warranties are equivalent. They're probably worth exactly the same, but most people will pay more for the second type of warranty. So that's called pseudo certainty effect. You're willing to pay more to get some certainty on what is being covered. And here's another case here on this slide where they're talking about vaccines. And would you be more willing to take a vaccine that maybe only protects you up to 50%? Or let's say there's a disease or a virus going around and there's 2 strains of the virus, let's say, all right? And would you be willing to get a vaccine that has a 50% probability of covering both viruses? Or would you prefer a vaccine that with 100% covers one of the viruses, one strain, and doesn't necessarily cover the other one? And most people would pick the second vaccine because of the certainty that it would protect you against one of the viruses, even though the 2 types of vaccines would be equivalent in terms of your protection. All right, so this is called pseudo certainty effect. Now, all these types of biases that are mentioned in this chapter were developed by these 2 people, Tversky and Kahneman. Kahneman, by the way, won a Nobel Prize in economics for these ideas. And he used the term heuristic, which are basically the types of mental rules that we use to come up with our probabilities, our personal probabilities. And many of these rules distort the true probability. In other words, we either are overestimating or underestimating the true probability. All right. So one of them is called the availability heuristic. All right, availability heuristic. And the fact, and one example of this is with this one that's mentioned in the slide here. When we were talking about what's more, which causes more death, homicides or diabetes, and Julie had mentioned this idea that, well, most people would pick homicide. It's more prevalent because it's available to us through the media. See what I'm saying? Our attention is, so availability means that we're more aware of it. And therefore we overestimate the probability of deaths by homicide. And because we're not aware of diabetes so much, unless again, we have family members who have it, we probably underestimate the number of deaths from diabetes. This is based on this so-called availability heuristic. See how we're doing with time? We've got 10 more minutes. I think I can get through most of this in 10 minutes. Risk perceptions are also distorted by having people vividly imagine an event. So very clever salespeople, many times, you walk into a store, you're buying something and they want you to buy a warranty, right? And I don't know how many times I've been told this particular phrase here, all right? So suppose that you're buying a warranty on your new car for some, let's say an air conditioner in your new car. I don't know why there would be, well, let's assume there's a warranty on the air conditioner part of it. And the salesperson will say that consider the fact that if your air conditioner fails, it will cost you $2,000 to replace the air conditioner. All right, then maybe they'll just throw a number out like that to you. Well, that's supposed to get you motivated to say, all right, $500 is less than $2,000. Let me buy the warranty. Seems reasonable. The only problem is that the probability of the air conditioning failing is very, very small. So the expected value of this warranty, all right, it's not worth buying this warranty. All right, it's not worth buying it because when you look at the actual cost over the long term, it's very small because the probability of the air conditioner failing is very small. When you do the expected value calculation, a very small probability times $500 or excuse me, times whatever the air conditioner costs is actually much smaller much smaller than the warranty costs. So warranties aren't worth it usually. And most people, but the salesperson tries to convince you to buy it based on this false comparison. Look how much more it will cost you if the air conditioner does fail. And they fail to mention how unlikely it is that the air conditioner will fail. Another way of influencing people is what's called anchoring. What's anchoring? Anchoring means you give a person a starting point, a baseline from which to make a comparison. Here's a question about nuclear war. All right. What is the chance of a nuclear war between the US and, well, let's say Russia now? Soviet Union doesn't exist. So let's say that two different people give two different answers. One person might say, all right, do you think the chances were higher or lower than 1%? Somebody else might say, well, do you think the chances are higher or lower than 90%? Well, if you give the person the 1% value, their answer, if they have really no idea, they're going to give you an answer closer to 1%. They'll give you a low percent. If you ask the question in terms of 90%, they're going to tend to give an answer closer to 90%. If you don't give them an anchor at all, if you don't give them any numbers, then they're going to be all over the place. And most likely the answer is going to be somewhere 40, 50%. So this is called anchoring, where you are giving a person a baseline, whether it's true or not, from which to actually answer the question, especially questions where the person may have no idea what the answer is. Another one is called the representative heuristic. What is that? It says it leads people to assign higher probabilities than warranted to scenarios that are representative of how we imagine things would happen. Okay? And that would be the case where you are describing somebody. You know, these scenarios that we were looking at earlier, where we were describing individuals, and we were saying, well, given the knowledge of chapter 14, well, it's a subset of this other thing, but most people wouldn't think that way. They would look at the scenario and imagine it in their head and think, is that more likely? And most likely they will come up with a higher probability than they should. And this is called the representative heuristic, because the way it's described is they can imagine it as representative of the actual result. In addition to this is something that's connected with this is called the conjunction fallacy, because many times you can look at two events that occur simultaneously, and because you are considering the fact that it seems in your mind more likely that those two events occur together as opposed to not occurring together, you might give a higher probability of the two events occurring together. Now, you know that if the events are independent of one another, we multiply probabilities. And one of the mathematical certainties of multiplying numbers that are between 0 and 1 is that when we multiply two numbers between 0 and 1, we're going to get a smaller number, right? For example, 0.9 times 0.9 is 0.81. That's smaller than 0.9. Normally, when we have numbers that we multiply that are bigger than 1, the result is a number that's bigger than both numbers. But that's not true with probabilities, because probabilities are between 0 and 1. When we multiply them, we get a result that is smaller than those probabilities. Okay? Smaller than the biggest one, at least. And therefore, somebody not knowing anything about probability might look at the conjunction or two events coming together and thinking, hey, that's pretty likely based on this representative heuristic, right? It seems pretty likely. Therefore, I'm going to give it a higher probability than if they weren't together. All right. So in both cases here, we would end up with our personal probabilities being larger than they really should be. All right, here's an example of the representative heuristic. This is actually a famous one that Kahneman and Tversky published. So now what they did here was they gave this this information out to people who had not studied statistics. They don't know anything about statistics. And they said, Linda is 31 years old. She's single, outspoken, very bright, majors in philosophy. As a student, she's deeply concerned with issues of discrimination and social justice, and participated in anti-nuclear demonstrations. So they want you to say, which of these two statements are more probable? Linda's a bank teller, or Linda's a bank teller who's active in the feminist movement? Well, due to the representativeness, right, heuristic, you read this and say, all right, she's an activist, right? So you go down here and you look and say, oh, option number 2 says she's an activist. Well, that's more likely than the fact that she is, she's just a bank teller. That's how people would reason this. And they would give a higher probability to option 2. Now we know from chapter 14 that option 2 is a subset of option 1. But most people don't think that way. Most people think option 2 is more likely because of what they've read here. They've read that she's an activist. Therefore, it seems pretty more likely that she's more than just a bank teller. She's active in the feminist movement. Seems pretty likely she is. So they would say option 2 is more likely than just option 1. Most people, by the way, when they think of probabilities, and I find this when I've taught probabilities to introductory classes, they tend to add probabilities. They don't multiply them. People tend to add them. When you add probabilities, you get a bigger number. When you multiply probabilities, you get a smaller number. Okay, so they think they're being logical. And actually, in this study here, Kahneman and Tversky found that 86% of the people felt that the second statement was more probable than the first statement, based on this description of Linda. Okay, so logically, we now know the answer should be 1. But most people would pick 2. Large number of people would pick number 2. Also, this idea of forgotten base rates. This was the case of the engineers and lawyers. Remember, we read about that other person, right? And most people would have just said 50-50, right? And they would ignore the 30 and 70. But you guys have already been trained. You already know not to ignore the baseline numbers that are given in this scenario, the 30 and 70, right? Now, here's another example. Dick is a 30-year-old man. He's married with no children. A man of high ability and high motivation, he promises to be quite successful in his field. He is well liked by his colleagues. Hey, that could apply to both an engineer and a lawyer, right? And most people would say, all right, 50-50 chance he's an engineer. They would. They would have forgotten about the 30 engineers and the 70 lawyers in a group of 100. They would just say, I don't know, 50-50. And then in this chapter, we talk about optimism. People who are overly optimistic tend to overestimate probabilities. Actually, overestimate their own abilities, right? Every single person in this class would say, you're better than average. I'm a better than average driver. Well, if we just look at the driving ability of everybody in this class, we cannot say everybody's a better than average driver, because there's going to be some drivers that are better than average and some that are not. But nobody wants to be called a below average driver or mediocre, or whatever word you want to use, right? It sounds terrible, right? Everybody's going to live past 80 or 90, right? You know, if I drink formaldehyde, I'm going to get slightly sick. If I know COVID's out there, right? I'm not going to get it. I feel great right now. I'm going to run around the block. I'm going to run around the block without a mask. You know, I don't care how many people around me, because I feel great. I'm not going to get COVID. That's overconfidence. You're this is perfect, right? In the circumstances we're in, some people are so over optimistic and overconfident, they underestimate severely the probability of certain events happening. All right, no explanation needed for this, right? We're living through times just like this. Here's another thing. This applies to this time also. Reluctance to change. Now that, I mean, the COVID situation, right? It's the same thing. If people are convinced that COVID's a hoax and the probability of it's practically zero of somebody getting it, I don't care how much evidence you throw in front of them, they're not going to change their the chances of themselves getting it. That's this idea of conservatism, reluctance to change. Even given new evidence, they're willing, first of all, they feel defensive, right? They feel like they have to protect their integrity and all that sort of thing. All right. And then overconfidence I just talked about. And then these are examples here. The rest of this chapter deals with calibrating and making changes to these things that could affect your personal probabilities. You can read through it, but we've gone through all of the different biases that are mentioned in this chapter. So I've run a little bit over. I think we're done for the day. Are there any questions about what we covered today? Anything from chapter 14 or chapter 16? And if there's not, then I just want to reiterate that there's a quiz next Monday that will cover chapters 14 and 16, basic definitions once again. And chapter 17 will be covered, excuse me, yeah, chapter 17 will be covered also on Monday. And then on next Wednesday, I will cover 19, which is brand new material on sampling. And I will also be reviewing with you this computer software that we're going to be using for the rest of the course. It's completely free software. It's called StatKey. And I'll be showing you how to use it, beginning to show you how to use it. So make sure you are in class next Wednesday. Of course, I'll be recording it too, but it's always better to be in class. All right, any questions, comments? Are we good? Good, all right. So I will see you guys. I will shut off the recording and I'll see you